Good morning, everyone. My name is Patricia Dugan. Thank you for coming to Coffee with Cluster One yet again. Coffee with Cluster One is a webinar that's been crafted for data scientists, developers, and deep learning aficionados. We welcome you to hang out with us. Today is a really exciting day. We have Ryan Sepassi with us from the Google Brain team. He's going to talk about Tensor2Tensor. And we encourage you to ask questions so we can answer them at the end of the webinar. So what we'll do is, if you please enter them in the chat box, we will compile them and then respond to them at the end of our webinar. So if you have anything that's not webinar related, please go ahead and direct message me on the chat. And until then, we welcome you. We hope you're drinking coffee, tea, or something else fun, and enjoy the session. Off to you, Malo.
Hi, so my name is Malu. I'm a co-founder and product lead here at Cluster1. So we created Cluster1 to make AI development at scale easier and more efficient. And so part of what we build is a platform that makes that. We also offer AI solutions to our customers, and we also try to organize things like this webinar where we invite people with expertise like Ryan to present about their work and explain how to do AI at scale. So Cluster1 was founded in 2016 with this mission, and in December 2017, we raised our seed round with the Allen Institute for AI in Seattle. And we now have offices across the US and Europe. Cluster1 was built in order to accelerate AI research by enabling data scientists to take advantage of scalability and distributed training to speed up model development. We offer a zero DevOps platform so that you can focus on the modeling and not on the setup. And we also offer infrastructure freedom, meaning you can choose any infrastructure, be it on-premise or cloud offerings such as AWS and GCP. So the way our platform looks like is you have access to a dashboard and a command line and an API to run any machine learning app. So that can be TensorFlow, PyTorch, Caffe, Jupyter Notebooks, and tools such as TensorBoard. And what Cluster1 does is it takes care of all the OS level parts such as Kubernetes, orchestration, account management, and it allows the data scientists to stay focused on building models and not setting up all those things you need to do machine learning at scale. And this platform runs on top of any compute infrastructure, so AWS, Google Cloud Platform, Azure, etc., or on-premise, uses any form of storage and any code artifact. So it gives you this flexibility about what tool you can use for the best of your use case. So I will now hand it over to Ryan that will present Tensor2Tensor, and I'm very excited about this.
Great, thank you, Malo. Let me get the screen shared. Thanks all for attending. Let's get started. So I'm going to be presenting on machine learning with Tensor2Tensor. So I'm Ryan. I'm from the Google Brain team. The Brain team is an awesome team at Google. Our mission is to make machines intelligent and improve people's lives. And we do that mostly through publishing research papers and related software, including TensorFlow, which many of you I'm sure use. So I'm going to tell you a bit about Tensor2Tensor. Right, disclaimer: all views are my own, not Google's. I'm here in a, everything's unofficial, and Tensor2Tensor is not an official Google product. So let's talk about Tensor2Tensor. I'll try to leave about 20 minutes for your questions so we can address some of the things you're interested in. Tensor2Tensor is a really big collaboration. All of these people have contributed to it in significant ways. And I'd like to call out Lukasz Kaiser in particular, who originated the project and is probably the person most responsible for for its current state. We also wrote a paper. It's up on arXiv, so you can go check that out. It's called Tensor2Tensor for Neural Machine Translation. Although Tensor2Tensor does more than machine translation, this paper is a good overview of some of the architecture internally. And we're on GitHub. So we do all of our development out in the open. We try to actually push every commit internally out externally pretty much as it happens. And then we release on PyPy, so you can pip install Tensor2Tensor. We do that about every 1 to 3 weeks. As you can see, we've got over 50 releases so far. There are 70 contributors, both internal to Google and external. There's a rather active community now around Tensor2Tensor. Yeah, so we welcome open an issue or a pull request, particularly to add a model or a data set. As you can see, we have over 4,000 stars, nearly 1,000 forks. So, and there have been other tools that have built on top of Tensor2Tensor in academic communities and other places. So we're very excited about that. And yeah, so what is Tensor2Tensor actually? It's, we try to kind of make it a batteries included toolkit for machine learning research and practice. And so what that means is that we have a library of models, 45 and growing currently, hyperparameter sets for those models. We have data sets, everything from MNIST to many translation tasks, sequence tasks. There's 193 and counting, and hopefully I'll show you a list later on. And then there's model and training components like, of course, there's all of TensorFlow, all of Tensor2Tensor is built on top of TensorFlow. But we have additional components that are maybe a bit more research oriented, and I'll try to call out some of them as well. And then the second part is that there's scripts to sort of tie all this together. And 3 of the main command lines are to generate data sets, T2T data gen, to train and evaluate models, that's T2T trainer, and then to decode from trained models, T2T decoder. And we'll get to a short demo later so you can see some of this functionality in action. And then we have a focus on sequence tasks, although we do many other things. The transformer model, which we'll talk about a bit, is the reference implementation is within Tensor2Tensor. And a lot of the research work that many of the researchers who work on Tensor2Tensor, who use it and work on it, focus on sequence tasks. We also focus on spanning scales. So Google, it's a very large scale place, but research, you want to be kind of fast and iterative. And so that means that Tensor2Tensor supports everything from, operating in a collab in TensorFlow's eager mode, where you have, instant execution, to a local GPU, to multi-GPU machines, to distributed setup. We support both data and model parallelism across devices and machines. We support hyperparameter tuning, and we run many of our models on Google's new chipset, tensor processing units, or TPUs. And we also focus on research. Now, TensorFlow has done a really good job in the TensorFlow ecosystem of bridging a lot of research to production. And so that means that a lot of Tensor2Tensor models are actually quite easily exported to the TensorFlow servings format, so you can actually serve these models in production. But the user experience, we really focus on sort of researchers' productivity. And that usually means that it should be easy to try things out. It should be easy to add new models and try them on many different data sets and have a lot of niceties sort of baked in. And there have actually been over 10 papers published with Tensor2Tensor so far. And you can find them at the bottom of our GitHub README. It kind of all started with this attention is all you need paper, which presented the transformer model, which we'll talk about a bit later. But as you can see, there have been many others. Cool. So at this point, actually, I think it would be cool to just see some of Tensor2Tensor in library usage in action. And so there's a Colab notebook here. And so I'll just connect. And I just want to check with the organizers. Can I just get a thumbs up that all the presenting is hooked up and everybody can see everything? Awesome, thank you. So this is a collab, which was linked from the slides, so you can get to it later. And what's nice about this is Google actually has this has released this thing called Colab. You can get to it at colab.research.google.com. And it's basically a free, accessible, Jupyter notebook that's sort of hosted in the cloud and has a GPU attached. And so it's pretty cool. And so a lot of times, many people within Google, including myself, we kind of use this to sort of just play around with things. And you have full access to sort of the command line here, so you can pip install things. And so here we'll pip install Tensor2Tensor and TensorFlow. Oh, and I should say that what we're gonna do is what every mini machine learning demo in recent history has done, which is we're going to train an MNIST model. But we're going to define just like a simple custom model, and hopefully this will just show you sort of some of the key components, and I'll try to point things out that about Tensor2Tensor as we go. We'll grab some imports here, and the Tensor2Tensor imports are here. These are just various components. So as you can see, we import models and problems, and so all of our data sets we call problems. And so when you import models and problems, all those models, the 45 models and the 193 problems, when you import problems, all get registered. And then there's some various kind of common components within Tensor2Tensor. We have these layers that are useful for many models, and some various other things. Some of you may be familiar with TensorFlow's eager execution mode, and so this TensorFlow kind of typically runs in this delayed execution mode that we call graph mode, where you build up a graph and then you kind of launch it in a runtime and then interact with it. But eager mode makes it that you can it's kind of like NumPy style execution. So, when you do tf.add, you just immediately get something back. And so that's pretty nice for interactive kind of small scale usage. Okay, cool. So I think I ran that. So let's take a look at, nope, did not run it. Sorry about that. Great. So we can ask the registry to list all of the problems. And so this is a list of all the problems within Tensor2Tensor. And as you can see, there's a set of algorithmic problems, there's some genomics problems, there's actually more recently some reinforcement learning problems, particularly for model-based learning. There's a lot of image problems, CFAR and ImageNet, MS COCO. We have image-to-image problems where you're trying to, do super resolution or something, language modeling, speech recognition, and of course, lots of translation tasks. So we're going to grab the MNIST problem, and that call is right here. And so that gives us the MNIST problem, and problems have kind of two main, methods. One is to generate data. And so that's what we'll do here. And so this way, users, you don't have to worry about, especially with all these public research data sets, you don't have to worry about the pre-processing. You don't have to worry about getting it into a common format and all of that. You just fetch the problem, call generate data, and it, as you can see, it actually goes, downloads the data from wherever it's hosted. In this case, Jan LeCun's website for MNIST, and it kind of pre-processes it and puts it into a common format that's suitable for performant training. In this case, almost all data sets in Tensor2Tensor write out to disk TF record files with TensorFlow example protocol buffers, and then the second kind of main method for problems after you've generated the data, which now exists on disk, is the dataset method. And so this is sort of, the other end, you generate the data to disk, and then the dataset method returns to you a tfdata.dataset, which is TensorFlow's kind of newest input pipeline software or module. It's pretty great. I encourage you guys to use datasets. It's definitely the kind of nicest, easiest, and most performant way to pipe data through. So TF Eager has iterators that can kind of eagerly go through these data sets, meaning, kind of leaving aside the delayed graph execution, and you can actually, look at the data kind of in a streaming format. So here we can just immediately start looking at some MNIST images. So we've just grabbed the next image from the data set, and now we're just pulling out inputs and targets. Almost all tensor-to-tensor problems, we try to keep them in a format that it has normally two keys, inputs and targets. Of course, there are some problems that have multiple, but almost every problem will have inputs and targets, so it's kind of, we try to keep things reasonably uniform so that as you use the library, you can sort of, you can kind of generalize as you go. So cool. So we can just take a look at some images. These look like MNIST images. Great. So now we want to train a model. So like I said, we've got a lot of models. Here's a list of all the registered ones. We've got autoencoders, language models. There's LSTM variants in here. Image models like ResNet and RevNet and Shake. And then you can see there are many variants of the transformer model, which is the really powerful attention sequence model. Great, so we'll actually just create our own model. So all models in Tensor2Tensor are subclasses of T2T model. And most models actually only define a body method. And what this does is it takes sort of a dense float tensor input, which is always given as a dict of inputs, and it returns a kind of float dense tensor output. And what you don't see here is sort of some methods, sort of the bottom of the model, and these are actually methods of T2T model, and then the top and the loss. And the reason is because every problem in Tensor2Tensor defines every problem defines for each of the features, including the targets, a modality. And modalities are sort of feature adapters. So they tell you, for example, like there's a symbol modality, and the symbol modality .bottom method will embed integer tensors. And so that means that when you're trying a model on a problem, you don't have to worry about kind of getting the input features into a format that your model can use. And so common things like integer symbol inputs will automatically get embedded because the problem specifies that the inputs feature is of type symbol. And so the default bottom method in the model will automatically call that the feature adapter's bottom method the symbol modality. Now in this case we're running MNIST, and so it's an image, and so with an image you actually don't really have to do much. You just have to convert it to float tensors. So in this case, the features inputs is a 4-dimensional tensor, of size batch, height, width, and then channels, which in this case is going to be actually I think with MNIST is just one. But anyways, so here we just have a simple 3-layer convnet, and then the top and the loss similarly are default to the whatever the target features modality is. And so in this case, MNIST, it's a classification problem, and so the targets have the class label modality, And this is essentially just going to make sure that the top projects whatever the output of the model body was to the number of classes. And then the loss will have, in this case, in a multi-class classification problem, softmax cross entropy. And for the most part, when you define, when you use any of the problems in Tensor2Tensor, you can sort of just trust that all of these things are already kind of taken care of. And so you can just focus on the part that really you probably care about and matters, which is the body of the model, like where you're really trying to find an architecture that works really well with your problem. Cool. And then the next part is to actually instantiate this model with a hyperparameter set. All of our hyperparameter sets are defined in code, and maybe I'll show you what a definition looks like in a second. But we instantiate the model in training mode, and we set up some things for the training loop. We repeat the data set so that we'll get like a nice big stream of examples, epochs over the data, and we'll batch it. Eager mode gives you this implicit value and gradients when you define a loss function, so that it'll actually update variables as you go. And then here in this next cell, we've got the actual training loop. And so let's kick that off. And it'll do 500 steps. And you can see it's a pretty standard loop. We're iterating over the data, and we're getting the loss for that batch, and then we're applying the gradients with the optimizer. And we're just going to do this, log some stuff out, and we should see. Sorry about all these superfluous log statements; those will go away in the next release. So we should see the loss going down, and sure enough, it is. Step 200, N1, we've got 0.6, 0.4. All right. And so this is all library usage. So, we're in a collab when we're just kind of using the modules within Tensor2Tensor to sort of build up our own, training loop and evaluation, which we'll do in a second, and model and all of that. And so this is often where you might start. But what will happen is, you'll save some of this code to some files and, import it within the Tensor2Tensor library. And you will then actually use a lot of the command line utilities, which I'll kind of show off in just a second. And let me just get this kicked off. And so here we'll actually now evaluate the model. So the model finished training, it did 500 steps. And now we can actually just grab the eval data set just as easily as we grabbed the training data set. We set the model mode to eval, and then we create some metrics. And as you can see, that Tensor2Tensor has a lot of common metrics sort of registered or defined in a way where it's like really easy to actually just grab the things that you need. Problems actually define what the eval metrics that they need are. And so normally when you run T2T trainer, which is the kind of main command line scripts to train and evaluate models, you won't even have to think about what metrics to be using for a given problem. And so here we iterate over the eval data set for a couple hundred examples, and we make predictions from the model, and then accumulate the metrics over all of these batches. And then finally, we're going to print it out. And so hopefully we'll find that we'll have gotten some good accuracy. And we find that the top 5 accuracy is 100%, and the per example accuracy on average was 99%. So that's pretty good. So there's the MNIST demo with Tensor2Tensor in library usage with eager mode. And so this is kind of like one end of the spectrum of scale. This is very small scale. It's just in a browser, and you happen to actually have a local GPU kind of connected here, but it's really iterative, really fast. You can try things out really quickly, yeah, so that's a pretty nice kind of usable thing. And of course, we just rely on a lot of TensorFlow's eager machinery to give us that experience, and we just kind of make sure that we interoperate with all of it. So I also wanted to show you some command line, and actually I am going to, just for a second, stop sharing the screen, and we'll resume shortly. Sorry for the delay. I failed to get a couple things set up just before. Okay. Hey, Malo, how's the screen share coming through? Good? Okay, awesome. Thank you. Okay, so on the command line, what might some of this look like? So we tried to make the user experience reasonably nice. So let's say we wanted to train a translation model, and we want to train it with the transformer. And typically we'd first generate the data. Now I've already done that, and the command would look like this: T2T data gen. We'd specify the problem that we want to generate the data for. In this case, we want to generate English-German translation, the WMT data set, and we have already on disk, or we have a problem that will generate on disk with a vocabulary of 32,000. And we would give it a data directory and a temp directory where it'll download things to. And so I've already gone ahead and run that beforehand. And so if we take a look at that data directory, we'll find that we have 101 files. So we've got one eval shard, and then we've got 100 training shards here. And we'll also find that there's a vocab file. And we're going to be using this one here, this 32,000, approximately 32,000 tokens in the vocabulary. And so that's nice because that automatically got created. We don't have to worry about it. And here's how we would train the model. So T2T trainer is kind of the main workhorse, and it normally kind of requires a triplet of model, hyperparameter set, and problem. So here we'll train a transformer model. We'll train it on that same problem, translate ENDE WMT32K. And we'll use the hyperparameter set transformer base. And all the hyperparameter sets are defined in the same file as the model definition. So if you went to transformer.py in Tensor2Tensor, you would see you'd see a pretty huge number of hyperparameter sets. And almost always the one that you should kind of start with is the one that ends in just base. And the trainer takes a few more commands. We'll just train for 5 steps. Train steps is 5. And we have to provide a couple data directories. We have to provide a couple directories. One is the data directory. And the other is an output directory where all the model checkpoints and TensorBoard event files and things will go. So here we'll just create a training webinar. Okay, cool. So let's kick that off. And so this trainer both trains and evaluates. And so we'll see eval metrics at the end. And we can set it to only train or only evaluate. But typically we, you know, especially when you're running kind of locally on a GPU or on a few GPUs, you want to see it switch. Although whenever we run large training jobs, we typically launch a trainer that just trains and then separately have an evaluator that's reading checkpoint files and occasionally and evaluates. So we saw you know, various logs about, you know, what the devices look like. We see the Tensor2Tensor model actually building, and now we see the TensorFlow session starting up and actually running our model. We see the first log for the loss and the step, and it's finished 5 steps. It's saving the checkpoint, and now it's actually going through evaluation. So we can see that the T2T model mode has been set to eval. And so that means like a lot of dropout parameters and things like that get set to 0. And after 5 training steps, we don't really expect to see very good evaluation metrics. But as you can see, it's going through the evaluation data, and it logs out a bunch of evaluation metrics that are, you know, relevant to this problem. For example, accuracy or accuracy over the entire sequence. And then we have metrics like the main one we use for translation mostly is negative log perplexity. And then for the real full evaluation, we would report blue scores. Yeah, so what I'd also like to show you is the T2T decoder. So let's say we had a trained model, which I have here as transformer END v1. And this model is the base transformer. It's exactly what we just trained. It's just been trained for a lot longer. And so there's a command T2T decoder. It takes the same triplets for the model and the hyperparameter set and the problem. And here we'll provide the same data directory so that it can grab the vocabulary file. And the output directory will set to that checkpoint that we have in the already pre-trained checkpoint. And we have actually a decode interactive mode, which is nice because you can just kind of type right into the terminal and see predictions just sort of interactively. Great. So it seems like we're ready, and so we can ask it to translate "Hello World." And remember, this is English-German, so let's see how it does with that. And it's getting the model all loaded up, and it says "Hallo Welt." I don't speak German, so I don't know if that's a great translation, but you know, there's Google Translate, and so here's a sentence. And we'll ask it to translate into German. And this is the translation that Google Translate you know, gives us. And Google Translate's, you know, a pretty good system. So let's see how our model, which was trained exactly with the trainer command that we saw previously, does on that. So let's copy this sentence. And we get, I won't try to pronounce it because I don't speak German, but it looks pretty much like what we got. So compare that for yourselves to the translation we see on the right. And I think that's pretty good. So anyways, that's pretty much like a state-of-the-art, you know, translation model that you can train, if you grab, an 8 GPU box and tensor to tensor, you can get that in reasonably short order. Cool. So that's the end of the command line demo. You can also easily define your own text-to-text problem. You can define your own problem and any kind of problem by subclassing problem, but there's a set of text-to-text problems that are particularly easy to define. All you have to do with text-to-text tempter is just put inputs dot. You would have to just define your inputs and targets in files and put those in the temp directory. These are the 4 files that you need to define. And then you run T2T data gen with the problem text-to-text tempter, and it'll get your files, it'll get everything in the right format that you can just immediately run a T2T trainer on it, which is pretty cool. And you can take a look at the text-to-text problem more generally, or the base problem class to see how to define your own problem, any kind of problem. Okay, cool. So I want to briefly describe the kind of star model in the tensor-to-tensor stable, which is the transformer model from this paper called Attention is All You Need. And the paper's on arXiv, and you can find it there. And this is a diagram of the overall architecture. And I'm just going to focus on one piece, which is these orange boxes where you see multi-head attention. So I'm just going to focus on the attention component and describe why it's a really powerful module for sequence modeling. So the task is we want to model some long sequence, usually variable length. We don't have a fixed known length of that sequence. And it's a bit of a challenge because we have this vanishing exploding gradients problem, both in time and depth. And so this is a problem in general in deep learning, where very deep models are very hard to train because as the gradient kind of flows through them on the backwards pass, like as you take the gradient of the loss with respect to all of the weights, especially the ones down, kind of at the bottom of the model, it's going through a lot of kind of multiplicative, effects. And so it can get much larger, it could get much smaller. And that can be a problem for training. And so sequences are sort of like that because you're backpropagating through time. And so the time actually ends up being kind of like a depth, like in a, let's say like an image model. And so the workhorse for sequence modeling since it first came out in the 90s was the long short-term memory, which got around this vanishing exploding gradients problem through a gating mechanism within the LSTM cell. And so you can see here from Chris Ola's collab, kind of a nice diagram of what this looks like. I encourage you to read that blog post to understand LSTMs better. And so this was really the state of the art in all sorts of sequence tasks and natural language tasks for quite a while, until DeepMind had this sequence convolutional neural network paper. And so this was like WaveNet and ByteNet. And as you can see, the model is quite different. And so you see a diagram here on the left of what the sequence processing looks like. And at each layer, you essentially kind of look at a temporal kind of receptive field. So like kind of but as you can see that at each layer you go up, it begins to skip. And so by the time you get a few layers up, if you look at the orange layer, that last orange circle, it's really being affected by not only the things kind of directly below it, the time steps, the time step that it's computing over, but it's also having input from time steps very far away. And that's pretty nice. And then the attention mechanism actually now gets input at every time step from every other time step. And so that collapses down the kind of distance, the path between time steps to one, whereas the LSTM, it would be N, where n is the number of time steps, and in the sequence convolutional neural network, it would be logarithmic. In the attention, it would be constant. And that's really nice for training when you need a lot of interaction between distant time steps. So, and then there are variants for this is the encoder, where every time step attends to every other time step. Then there's the decoder, and of course for the decoder, when you're actually predicting, you only want to look left. You only want to look at the things that came, before you. You can't see into the future. And then connecting the encoder and decoder, you have encoder-decoder attention, where the attention is over the encoder. And so the formulation is this is the actual equation that computes dot product attention. And so you take a hidden activation, project it into three parts: query, key, and value. And then the queries and keys get dot producted together. And the value of the dot product determines the weight of the attention on that time step. And this is happening, remember, for every time step. So every time step looks at every other time step and determines how much to attend to it. So this is pretty cool. And these are the kind of three types of models that we covered: attention, recurrent, and convolutional. And the complexity per layer has different characteristics. And so for attention, because you're getting kind of pairwise time interactions, the complexity scales with the length of the sequence squared. And whereas with recurrent and convolutional, they have different scaling factors. The second part, the sequential operations, is all about during training, how much do you have to wait for sequential operations to propagate? And so during training, you're feeding in the full known sequence. So it's sometimes referred to as teacher forcing, where you're not actually auto-regressing. You're not taking the output of the model and feeding it into the input. You're actually using the real next token as input. And so self-attention and convolutional have constant sequential operations, meaning you never have to wait for anything to propagate during training. Whereas recurrent architectures, you actually have to wait for the hidden state to propagate during training. And so that can actually, that slows down training quite a bit. And then finally, there's the maximum path length. And this is the length between time steps, kind of thinking about like the gradient path length and, or the information path length. And with attention, it's constant because each time step immediately refers to every other time step. With recurrent, it's linear in time because you have to wait until, at time step 1, it has to propagate through all of the, each hidden state until time step n. And then convolutional, it's logarithmic because you have this, at every layer, you have this expanding kind of receptive field. And so the bottom line is that with the transformer, which you see at the bottom, and the base model is the one that we were just training in the command line, you can see that it gets phenomenal BLEU scores. And so, the big model, the base model, which is quite small and can be trained on, a single GPU with a pretty reasonable batch size, gets, really great BLEU scores, beating almost everything that came before it. And the big model does beat everything that came before it. And note that the two models below the line are ensembles of models. And then you really see where the sequential operations, the constant number of sequential operations, helps you in that when you look at the number of flops that were used to train the models, these are the real numbers. You can see that transformer base takes, 3.3, which is really remarkable compared to, the models above. I mean, the numbers are massive. Cool. So you get, state-of-the-art model at a fraction of the training cost, which is really amazing. And so this is the command that we just ran, although with a much larger number of training steps. So at this point, I'd like to get to your questions. I just want to point out a few other cool things within Tensor2Tensor. And I'll just kind of breeze through these, and if they sound particularly interesting, please feel free to ask a question about it. With the supporting scale, like I said, we support both data parallelism and model parallelism, and mixture of experts layers, and there's an archive paper linked down below, are really cool because they add tons and tons of parameters to your model while keeping constant the number of flops, like the actual number of parameters that are being touched in every given step. And so as you can see, on the x-axis, we have number of model parameters, which were, and this is on a exponential scale here. So we have, at each tick, you're multiplying by 10 the number of parameters. And then you have a measure of quality where lower is better on the y-axis. And as you can see that, making these models bigger and bigger, and this is on a language modeling task, making these models bigger and bigger really helps. And, you really only begin to slow down and actually get a little bit worse once you exceed the number of training examples that you have. And so the blue versus the green is only 10 billion words with the blue, and then 100 billion words with the green. Yeah, so we like building really, really big models, and Tensor2Tensor sort of supports that sort of thing. We have like really easy launching on Cloud ML Engine, including hyperparameter tuning. And this is just, you run this locally and it'll sort of, launch it. Although I guess Cluster One provides a lot of these facilities. So, and then Cloud TPUs, same thing, just an extra command line flag, and it'll launch in the background, Google's Cloud TPUs, which are really powerful. We have lots of kind of utilities, data sets, and things for natural language processing, translation, and sequences, which is a lot of what a lot of the work that we focus on. We recently open sourced a data set for a recently published paper on Wikipedia summarization. And this was work that was led by Peter Liu and Mohammed Saleh. And it's called Wikisum Web inside Tensor2Tensor. And it's a really ambitious summarization task where we take all the contents of the references on a Wikipedia page. Those are the inputs. And then the outputs are the Wikipedia article, the Wikipedia page. And so it's sort of a really simple way of seeing summarization, and then like a really awesome data set where, we already have these great summarizations, which are Wikipedia articles. So let's see if we can learn, to do a mapping. Now, of course, this is insanely difficult because the input length is massive, and so is the output length. And so we took a crack at it, and we hope that more people come up with methods to do this sort of large scale sequence to sequence modeling. Noam Shazir and Mitchell Stern recently published a paper on the Adafactor optimizer, which is similar to Adam in that it has adaptive learning rates, except that the memory cost for those kind of, for the memory cost for using adaptive learning rates, in this case, is sublinear, whereas with Adam and other optimizers that use adaptive learning rates, typically it is linear, where you have, if you're maintaining these extra shadow variables, or scalars per variable. And so in this case, it has sublinear memory cost, which is really nice because that means we can use the memory for kind of better things like more weights or more activations. And that's it. So thanks very much for listening, and I'm happy to take some of your questions now.
So thank you so much, Ryan. This was super interesting, and we had too many questions for us to tackle in 10 minutes. So for the questions that don't get answered, we'll publish a follow-up post to tackle those. So I'll just sample from the questions I saw that were very interesting. And if we don't answer your question, expect an answer afterwards. So I'll start with a question on transfer learning. So if we're doing two different problems of different shapes, for example, I have an image classifier, right? And I want to transfer it to another problem. How does Tensor2Tensor facilitate that? How would it go?
Yeah, so if you wanted to do transfer learning, it's not something we support kind of out of the box. There's no command line flag that says, transfer learn from X, Y, and Z. But because you have kind of full control, like when you define your own model, you have, pretty much full control over everything that's happening. We try to, I didn't really point it out, but Tensor2Tensor is like, we've tried to make it so that, you have the framework around you so that if you want to kind of go the easy path and just use exactly what's there, you can. But, with a problem, you can just override the entire input pipeline, have whatever you want. And same with the model, you can just override end to end, exactly what happens. And so if you wanted to do transfer learning, the simplest would just be like, oh, I have some pre-trained checkpoint that I want to continue training from. And so for that, you would just, kind of put the checkpoint in the output directory. And then when you train, it'll just kind of continue training from that. And then more advanced transfer learning, you'd have to kind of like, wire it up yourself.
Great, thank you. So another question would be, generally speaking, for language generation tasks, what would you use as a metric except blue? And I guess as a follow-up, how do you define metrics in Tensor2Tensor?
Cool, yeah, good questions. So I would say that the simplest metric to use for language generation or any symbol generation task would be the perplexity metric, the like negative log perplexity, which is what is reported in Tensor2Tensor. And so that gives you kind of the, some measure of like the probability of that sequence as measured by the probabilities that were put out in like the softmax at each time step. And so what you want to do is you want to make those very likely. It's sort of like saying like, I want to, ideally I want to have this be extremely likely, like meaning I want the model to perfectly predict every token in the sequence. And sorry, what was the second part of the question, Malo?
Yeah, so this is more the sense question. On the more technical side, how do you define axiometrics?
Oh, a metric. Yeah, so I would point you to metrics.py in Tensor2Tensor. There's a file that defines all the metrics, and you can easily see what the API looks like. And so you can just add one there. And then if you're kind of just, so we're happy if you want to contribute a metric. If you want to just add it in your own model, then the T2T model class has a method called estimator spec eval, which is the thing that returns all of the metrics that the trainer should run during evaluation. And you can add whatever you'd like there. And you can see what the API looks like by looking at any of the other metrics.
Great. So there's a few questions about what exactly Tensor2Tensor supports, including, are there any unsupervised models built in, and is it possible to add some unsupervised learning tasks?
Yeah, so like language modeling is an unsupervised learning task where you just provide sequences and it just learns to kind of model the sequence. There's also, I believe, a kind of a basic generative adversarial network if you wanted to do if you wanted to do GAN training for images. We also have the image transformer, which can be used for unsupervised learning of images, where it learns to predict you provide images and it models it as a sequence task, similar to Pixel CNN, if you're familiar. And so, yeah, so any of these models. So like the transformer itself can be used as an unsupervised model where there's no encoder, it's just the decoder, and it's just learning to predict the next token. And so you can just provide unlabeled text and it'll just learn to model the text. And then image transformer, same thing. It'll just learn to model the pixels in images.
Awesome. So as I go through the question, I'm realizing that many of them are about how do I define this and this model in Tensor2Tensor. So I know you've briefly talked about this, but maybe can you go a little deeper into how do I contribute and how do I add a new model to Tensor2Tensor?
Yeah, so there are, again, kind of two things. If you just kind of want to be doing it on your own, or if you want to contribute to the library, both the model definition looks exactly the same. And so the model definition, let's see if I can pull up the collab again. So let me share. Great. So this is what many models actually look like in Tensor2Tensor. And so the transformer model is like this. It just defines a body method. It takes a features dict and then outputs a dense tensor that are like the pre-logit activations. And so if you wanted to define a model, it would look just like this. Of course, the body itself would be different. And so if it's kind of a standard model, like a model that's been published on, we'd be very happy to take that as a pull request to the Tensor2Tensor library. All the models are defined. So I can actually just pull up the, so all the models are defined in Tensor2Tensor models, and you can see, all of them here. And, we can look at, for example, shake and look for T2T model. And here is the shake model. And it looks, exactly like that simple MNIST model, the simple few layer convnet that we had. It's got a doc string linked to the paper. And then here's the body of the model. And then hyperparameter sets down below. Yeah, so I told you I'd show you what a hyperparameter set kind of looks like. And so they all kind of, pseudo inherit from basic params 1, and then, modify various things, add their own custom hyperparameters here. And yeah, and then you can just sort of, when on the command line, you can just say hyperparameter set, hparam set, shake small, or, any of these, shake quick. And so that's what a model looks like. And then the other piece of that is, so let's say you don't actually want to contribute into Tensor2Tensor. So I would point you to the documentation. There's a command line flag called T2T user dir. It'd be like T2T _USR _dir. And that allows you to basically define your own models and problems in your own local directory, and then have Tensor2Tensor, like the T2T trainer, kind of just dynamically import your library so that you can have your own models and problems, without having to actually go in and edit the Tensor2Tensor files.
Awesome. Great. So I guess this session is coming to an end. Thank you so much, Ryan, for attending. That was very informative, and everybody here loved it, and there were so many questions. So we will.
Yeah, sorry I couldn't get to everybody's questions. But yeah, thank you for hosting, and thank you to all the attendees for attending. And yeah, I hope it was helpful.
Great. And so to everybody, we will publish the list of questions and point you to the right resources. The Tensor documentation is great from my user perspective. So I guess it will answer to all the other questions that we didn't get to answer. So don't hesitate to keep in touch. We are organizing a series of such workshops. So stay put for what's coming next, and don't hesitate to reach out to me, and I'm happy to redirect the questions to whoever is fit. So thank you so much. And thank you, Ryan, for attending.
Cool. Thank you.
Thanks.
See you, everybody.
Bye.